Hi, I'm Professor Seth Chandler from the University of Houston Law Center, and today we're going to be looking at language models. It's part of the course Analytic Methods for Lawyers, but I've tried to create this video in a way that's accessible to a broader audience. We've invested a good deal of time in this course in developing an understanding of how modern language modeling works, and we've looked at embeddings, generally, word embeddings, and in the prior essay, we looked at attention layers and transformers, which, as I'm speaking this in 2021, is kind of state of the art. In this video, what I want to show you is some of the things you can do with these language models. We'll look at prediction of the next word, text generation, text clustering, and text classification. And to do this, I'm going to boldly use GPT-2, a technology which just a few years ago was said to be too dangerous to release to the public, presumably because it could create such realistic text that you could have deep fakes. Well, we'll take a look at that, and at the end of the video there'll be a bonus track on what's going on inside GPT-2. A disclaimer, I have taken many of the ideas from this essay from the official Wolfram documentation of the various neural networks that are in the Wolfram Neural Network repository. They did a good job, and although I'm going to modify them for clarity or for my own purposes, I'm not going to try to reinvent the wheel. All right, let's start with some text, and I'm going to take it from a Supreme Court case, Employment Division versus Smith from 1990. It's really about the extent to which generally applicable laws need to accommodate particular religious views. So we'll bring in this sentence here, which basically opens the opinion up. Launch the kernel, and there we go. We'll use text words, which we've seen many times before, to break this sentence into what Wolfram thinks are the words. There's a list of the words, and we're just going to take the first 15 words of the case, put a space between them, and then join it all up so that we just have the following. This case requires us to decide whether the free exercise clause of the First Amendment, and then GPT-2 is going to figure out what comes next. All right, so let's take a look at what's inside GPT-2. And to do that, I'm going to give it its name. You can get that name from the Wolfram Neural Network repository. Just Google that. And by adding parameters information, it's sort of going to give us an overview of what's available. So if we run that, what we learn is that we have a spinning beach ball. All right, there we go. And so we learned that there are two types of parameters. One is the task, one is the size. There are two permissible sort of variants of GPT-2. One simply does feature extraction, and we'll talk about what that is, and the other does language modeling, which is essentially prediction of next words. And then you can get three sizes. There's the small, this is the grande, and this is the venti size of the net. We're going to go at first for a language modeling task, and we'll go for the grande size. All right, so I'm going to specify that here by saying, get me the GPT-2 transformer. I want to use it for language modeling, and I want the 345 megabyte version. Now, I have a relatively swift internet connection here, so it's not going to take too long to download it. But if you're working with a slow internet connection, just be aware that this could take a minute or two to get. So let's actually look at what's inside this net chain. What we see is that we start with some input. We go through an embedding layer. And by the way, the input's going to be translated into a list of integers from 1 to 50,257. That's how many words GPT-2 knows about. It'll turn those into each of them will have 1024 vectors, so we're much bigger than our glove 50, or sometimes my little toy 2-element vectors. Then it's going to go into the decoder. That's that whole transformer attention block thing that we saw. And if this were the feature extraction part, we basically end here. But what then happens is you're going to capture the meaning of the sentence, as it were, in its last element. That's going to then go into a typical classification net, which is going to go to a softmax layer. You've seen softmax layers before, and that's going to make a prediction as to what word comes next. So let's actually see that in action here, and we'll take the Smith opening. That's the thing that we saw up here. This case requires us to decide, and let's see what it thinks the next most logical word is. This case requires us to decide whether the free exercise clause of the First Amendment requires. All right, that is in my opinion, a perfectly reasonable guess. It's not what Justice Scalia wrote. He wrote permits, which is somewhat of a different thing, but you can't fault GPT-2 for that. So that's its language modeling in its most basic use. Now, let's try and see what the 10 most likely next words are. And to do that, we'll again put Smith opening here so it knows what the seed is, and then I'll say get me the 10 most probable completions of that. So we have bars, forbids, provides, is, allows, applies, protects, permits, that's the one that was actually picked, prohibits, and requires. And so it actually picked the fourth most popular output. I thought it was sorting it this way, but it's sorting it from least probable among those 10 to most probable. And if you think about it, I think every single selection that it made would make grammatical and syntactic sense here. So I'm giving GPT-2 an A or an A minus for its work on this. Well, predicting one word is fine, but oftentimes we'd like to predict a lot of words. So to do that, what we're going to do is we're going to use nest. You know that nest keeps iterating over things. And the idea is we're going to make a prediction, and then we're going to feed that back into the language that we already have. And this is our seed. This is what we start with. This is our language model. This is GPT-2LM. This is how many words I want to go forwards. Temperature is sort of how creative you want GPT, the language model, to be. A high temperature means it's going to be very creative, and basically it's going to create gibberish in my experience. A low temperature also kind of seems to have weird things. I'm not clear why. And a seed is, there's randomness involved here. We're picking from random possibilities, and so this is to seed a random number generator. So let's get that into the kernel. And now what I want to say is take the Smith opening, use the GPT-2 language model, go forwards 10 words, stick with your common temperature of 1, and I have a little random seed here. So let's see what good old GPT-2 comes up with here. And as you can see, because I'm running this on a computer that does not have a compatible CPU, a GPU has a compatible CPU, but it does not have a compatible GPU, and as a result, GPT-2, which kind of, it's a giant model, it really would prefer that there be a GPU, and you'll see the performance here is not what I like. But let's see what it said. This case requires us to decide whether the free exercise clause of the First Amendment permits the federal government to require law enforcement practices that's not bad. I think that's pretty good. Now, it happens not to be what the case was about, but again, I'm not sure that's GPT's fault, and it may not have quite channeled Justice Scalia's style. But again, I think it's done a pretty good job in coming up with legal sounding text. Well, let's see what happens if we do increase the temperature here and we create a little more ability to be creative. And let's see what it comes up with today. There does seem to be elements of randomness in this. Requires us to decide whether the free exercise clause of the First Amendment alive next background because I disagree. So that is basically gibberish. So clearly increasing the temperature, that creativity is not going to work here. We could try decreasing the temperature, and in my experience, this is not going to go well. So let's see. Requires us to decide whether the free exercise clause of the First Amendment requires a balancing of religious freedom against, and then we sort of go off into something weird, ussy constitutionality. So it was doing well up until here, and then it kind of fell apart. And this, by the way, is very typical of computer language models. They tend to do well at first, and then they kind of collapse. And it's this ability to sustain the production of text that's really GPT-2 is much better than GPT original, and GPT-3, from what I could see from that dialogue earlier in the preceding video, was doing a lot better than GPT-2. All right, let's see. Well, I'm going to have it generate 5 sets of 10 words with a temperature of 1, and let's see, in general, how well GPT-2 does in replicating law speak. We can compare it to my 1L students. All right, I did pause the video because it's just painfully slow here, but let's look at this. Requires us to decide whether the free exercise of the First Amendment as ratified by each state would have, that's brilliant, excellent work. Requires us to decide whether the free exercise clause of the First Amendment requires a government interest as anticipated by the various, not bad. Authorizes anti-Marxist. Okay, so this is a typical problem of language generation where it gets stuck in a loop. It thinks the thing that most commonly follows anti-Marxist is anti-Marxist, and then it just keeps going on. So, not so good there. Creates a degree of immunity or limits the protection afforded. That's excellent. That's perfectly good. Obligates us to order and enforce current church disciplinary. That's fantastic. That could be a definite real opening of a case. So GPT-2, I think, is doing pretty well. Yeah, it didn't get the anti-Marxist thing right, but the others are pretty impressive. Let's see if it falls apart after 30 words instead of 10 words. Again, I'm going to pause just because you don't need to see it think. All right, let's see what we got here. Requires support for government treatment of abortion providers under these circumstances that is in a way that is consistent with the governing purpose of the statute prohibiting anti-pregnancy discrimination. Well, that would be a very interesting case. I'm not sure what that means, but I would say it did not fall apart after 30 words. I would say that's pretty darn good. Good job, GPT-2. All right. Let's see how it does on simpler concepts. I picked some language from The Cat in the Hat. The sun did not shine. It was too wet to play. So let's see if it thinks whether they sat in the house all that cold, cold, wet day. I sat there with Sally. We sat there, we two, and I said, oh, I wish I had something to do. Something like that. Well, I think it does better on legal text. The evening was endless on Santana's utilities over and over again. There was completely no excitement. This doesn't impress me. So, maybe GPT-2 should stick to law. I should add that people have used GPT-2 for question answering or text summarization, and frankly, I have not figured out how to do that, so we're not going to be covering that in this video. All right, let me switch to the other task of GPT-2, which is feature extraction. And let's see what that actually means. Let's download a little variant of GPT-2 GPT-2, whose task is feature extraction, and that's 345 megabytes, and we'll get a picture of what that looks like. All right, and it kind of looks like the language modeling task, except that the second half, where we're taking the last layer and then running it through a conventional classifier network, has been eliminated. Well, let's see what this actually does by taking the opening sentences of Smith and running it through our feature extraction variant of GPT-2. I guess I have some inkling it's going to produce a matrix because I'm going to ask it to make a little matrix plot. And indeed we do get a matrix. We see that it's 15 by 1024, 15 because there are 15 words, 1024 because GPT-2 wants to represent words as 1024 length vectors. So we're not in the realm of Glove 50 or my little toy models where we just had two values. We're in big data here. Let's see if we can figure out the meaning of sentences. And the idea here is there's sort of two ways we could go. But the concept is that, again, that last word, of the last contextualized word of a sentence or phrase is thought to embody everything that came before it, and so, because it had access to that. So it's kind of a proxy for the meaning of the sentence. So one way we could work with this is simply to add something called sequence last layer to our feature extraction network. And this is basically just going to take the last item. The other way we might have gone, by the way, is to go back to our language modeling task. And my belief is that if I simply just took this part of the network and cut out the classifier, I believe I would have accomplished the same thing. But in any event, it seems to be recommended by the Wolfram folks that we proceed this way by adding on, so that's what we'll do. And in just a moment, we will have a new neural network that has everything that the feature extraction had, but then we're just going to take the last part. Okay, let's see if we can test whether GPT-2, as modified in this way, can kind of understand the law or understand text. And to do this, I'm going to take some sentences from Katzenbach versus McClung. You may remember that's the Ollie's barbecue case on whether the 1964 Civil Rights Act was constitutional insofar as it obligated private businesses with only mild connections to interstate commerce to serve people regardless of their race. We'll also take more from Employment Division versus Smith, that case on religious liberty. And then finally, I'm curious as to whether GPT-2 can distinguish non-legal literature from legal literature. And so my non-legal sample is Pride and Prejudice. Why not go with one of the best books of Jane Austen? And we'll see what happens. So let's suck in some sentences from McClung. I'll use text sentences, which we've seen many times before, to break that up into sentences using some pre-constructed AI in the Wolfram language. We have our Smith sentences. By the way, I've taken out some citations here because I wasn't sure what GPT-2 would make of them, and I didn't think we wanted to be testing it on its ability to parse the Blue Book. So we'll also get some sentences here from Pride and Prejudice. It's actually in the Wolfram sort of example data. I'll take snippets of it, and then we'll break that up into sentences as well. So we've got it as a truth universally acknowledged, blah, 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 down to Mr. Bingley. All right. Now, what we're going to do is we'll join those sentences together, and we will apply sentence meaning to each of them, and that's going to give us an encoding of sentence meanings. So I'll run this. It is going to take some time, so I'll pause the video while it plows through. All right, we're done, and I guess there were 63 sentences involved, and it's come up with a 63 by 1024 matrix. Now, 1024 1024 vectors are pretty hard to visualize, even with radial axis plot. So let's reduce them down to length 2, and we are going to lose a lot of information in this, but my hope is that the sentences are still sufficiently different that we'll be able to notice something when we plot them, as you see down in the code below. So let's give that a try. And there we go. We've got our reduced dimensional representations of these 63 sentences. And now let's plot them. I'm going to color code. McClung is red, Smith is green, and Pride and Prejudice is blue. All right, so what do we see? We definitely see that the Jane Austen Pride and Prejudice material is off in its own world. So it is thinking that the meaning of those kind of sentences is different. We also see some distinction, like you can kind of draw a line here. I know I'm straining a little bit, but it does seem to be finding some distinction between the green Smith points and the red McClung points, although obviously the difference between them is much less than the difference between either of those two and the Jane Austen material. But again, I think that's pretty neat that GPT-2 can, even with all of these reductions in dimensionality, kind of see that legal language is different than whatever you want to call it, 19th century novel language, and that even cases about religious liberty, green, are maybe different from cases about the scope of Congress's power under the Commerce Clause, red. Well, let's look at a radial axis plot. Let's take those meanings and let's boil them down to 25 values. And now what I'm going to do is I'm going to take each of the sentences and I'm going to find, for each of their 25 components, I'm going to find their mean value. All right, so this is the code that's going to do it. This is not probably the best code I've written for this course, but you'll live with it. There. All right, so we've now found 3 length 25 vectors representing the characteristics, the 25 characteristics of each of the 3 authors, and we can you can see that the dimensions are 3 by 25. And now, that was the mistake. Let's use a radial axis plot to see if we can see any material differences. And kind of interesting. Here's what we see, I think. We see that for most categories, they're all the same. But for whatever this category is, Pride and Prejudice is very different from the legal language of McClung and Smith. And then we see McClung and Smith are really very different, except for whatever this component is, you're seeing a fairly substantial difference there. Whatever this component is, you're seeing a very substantial difference there. And whatever this component is, you're seeing a fairly substantial difference there. So, although, McClung and Smith, again, the 2 legal cases are much closer to each other than is Pride, which has this spike sticking out. So, is GPT-2 doing a decent job analyzing text? I think it's doing pretty well. I think that shows some intelligence. All right, now what I'd like to do is give it text from Chief Justice John Marshall. I'm going to take his opinion in Marbury versus Madison, extremely famous United States Supreme Court case, and text from Justice Joseph Story from his opinion in Prigg versus Pennsylvania about fugitive slaves. And I want to see, can GPT-2 figure out who's writing what sentence? Now, there are 2 things different from Marbury and Prigg. One is that Marshall's writing this one and Story is writing this one. But the other thing is Marbury versus Madison has a very different subject matter, basically the powers of federal courts and the powers of Congress to allocate powers to federal courts, versus Prigg versus Pennsylvania, which is about the Fugitive Slave Clause in the Constitution and states' rights, etc. So if it is able to make a distinction, it's not entirely clear which or both of those characteristics it's using, but it would be worth knowing whether it can make a distinction at all. And this is sort of the beginnings of an effort to, you might use this, for example, to detect textual forgeries, or to see who's writing various parts of opinions. All right, let's start by bringing in Marbury. I'm going to bring it in from the justia.com website. I have to do a little bit of cleaning because, they put page numbers in there and links and stuff that I don't want. So I'm going to be using a combination of regular expressions, which we studied just a few videos ago, string replace, string cases, and we'll bring it all in. All right, so there's Marbury and excerpted. There's a lot more because it's augmented terst. And we're going to do the same thing for Prigg versus Pennsylvania, again bringing it in from the Justia website. All right. Then what we're going to do is we're going to supervise learning, and we're going to tell it, hey, the sentences that are in Marbury come from Justice Marshall, and the sentences that are in Prigg come from Justice Story, and then we'll scramble it all up so that there's no order to the sentences. Like a Marbury sentence could follow a Prigg, and then another Prigg, and then a Marbury, and then two Priggs, etc. All right, so there we go. We've got this page thing, which is annoying because there's various page numbers that I didn't get out, but I don't think that's going to really damage our work. All right, so this part should be real familiar to you right by now. We're going to break up our data into training and test data, use about 70% for training. And now what I'm going to do is I'm going to use that sentence meaning neural network that we concocted to get embeddings for the left-hand side of all those rules. Those are the sentences. I have to use a CPU, and then we'll get what it predicted, or not what it predicted, whether it was really Marshall or really Story. I'm going to do this for the training data, and I'm going to do it for the test data. I am not going to do this live because this takes several hours because of the darn CPU thing and because GPT-2 is a beast. So what I did was, once it was done, I exported what I'd done to a file, and what I'm now going to do is simply import from that WXF file to get the stuff back without having to wait hours. And by the way, this is a very good habit to get into when you've done a lot of work and don't want to replicate it. Save it to a file and then have the ability to recall it. All right, now we're going to build just a simple classifier network. We'll use a net chain. We don't need net graphs. We don't need complicated encoders because the data is already numeric. And we're going to have a 100-node linear layer or ramp, a dropout layer to prevent overfitting, another 100-node linear layer, another ramp, another dropout layer, and then we're going to boil it down to 2. Why 2? Because it's just Marshall and Story. And then we'll softmax it at the end. And finally, we're going to say, hey, I don't want a number at the end. I'd like you to tell me, is this Justice Marshall or Justice Story? And then I want to see a picture of our little net chain. So there's our net chain. This should be relatively familiar to you by now. And now, the hard work's all done. Now I'm going to train it. So I'm going to train the data using the classifier head net chain. I want to get all the information back. I'll see if we're overfitting by using 10% for validation. And I'm going to use that training stopping criterion option to say, look, if you're not reducing the error rate on the validation set after 50 rounds, you've probably done enough. Use the darn CPU and go for a maximum of 500 rounds. And you're going to see that actually this part doesn't take long at all. Here we go. Bringing the data in, Training, training, training. Look, no overfitting. Feeling really good about this. And it stopped. All right. So let's see how we did. And we need to, I changed the capitalization of this at some point. All right, so we're going to use classifier measurements, which we can do on the trained net, which is what we're going to get out of this net trained results object, and we're going to look at the test embeddings to see how does this classifier do on data it's never seen before. And now let's look at the confusion matrix, the accuracy, the Cohen kappa, and the area under the ROC curve. And a very pleasant surprise. We've got 85% accuracy, which is a Cohen kappa of 63%, which I hope you remember means that as between how random chance would do, because we're mostly story opinions, story wrote a longer opinion, we're 63% of the way from random chance to perfection, pretty good, and the area under the curve is almost identical regardless of whether you consider Marshall or story to be the positive class. So I think GPT-2 did pretty well. It is able to discern which opinion is which. Now, a more interesting test would be to give it a lot of Marshall opinions, a lot of story opinions, so that it couldn't use subject matter clues as easily, and see how it does, and that I will leave as an exercise for some future student. So what we've seen is what GPT-2 can do, what it can't do, and it's not state-of-the-art in 2021. GPT-3 is state-of-the-art, but GPT-3 is not publicly available yet, and so we're relegated to state-of-the-art 2020. But I think what you see is both its strengths and limitations. And, to me, the real question is, have we reached the end of the line with these transformer architectures and 175 billion parameters, or are we going to be able to figure out something that's kind of smarter than transformers, that doesn't need all this stuff, and maybe can be trained without spending $10 million? If so, you can see the makings in GPT-2 and 3 of some pretty sophisticated language generation abilities. If not, we're going to be stuck in mediocrity. All right, so that is the end of the sort of required part of this video. It's also the end of our look at computational linguistics. But what I want to do is, for those who are interested, I want to do a little bit of a deep dive into GPT-2 so that those of you who are fascinated, as I am, about what the heck is going inside can get some insights. Okay, let's go inside GPT-2. I'm going to use the feature extraction variant of it. So let's just recall what the picture is. We've got input, and then it goes into an embedding layer, and the embedding layer feeds into the decoder layer, which is where all those attention layers are, and out pops some output, which is those length 1024 vectors. So I've broken up our survey into the embedding component and also input, and the decoder component. All right, let's see what that input component looks like. So I'm going to extract from GPT-2FE the input component. And we're going to see that's a net encoder. It's a slightly different net encoder. We've seen ones that have our type class. This one's a little different, but it is going to produce integers from length 1, values 1 to 50,257, which is basically how many words or linguistic things it knows about. Let's see how it works. Let's take this little encoder, and I'll give it some cat in the hat language here. I sat there with Sally. And we get a bunch of integers out. That is, it's going to translate each word into integers. And let's count. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. What's that sixth? And it turns out that GPT-2 does care about punctuation, which actually makes a lot of sense, because punctuation is often a good guide to knowing how much how far context extends, like materials before a period might not provide very much interesting context to materials after a period. Comma is kind of a weaker break, but the key thing is that GPT-2 does encode punctuation. And you can see this. Here's another Dr. Seuss book, One Fish, Two Fish, Red Fish, Blue Fish, which in the original doesn't have commas, but I stuck them in. And there you go, 50,246 seems to be the comma integer. Okay, so that's what's going on at the input level. And now let's look at this embedding piece here. So we'll take the embedding piece. Let's take a look at the full summary graphic of it, and also look at how it's represented in input form. That is, if you actually wanted to type this in. And here's a picture of what the embedding layer looks like. And you can see that you give it a sentence, which now consists of integers, and it's going to send that to two places. It's going to send that to this, what I happen to know is about positional embedding that I discussed in the prior video, and to a content embedding layer. And then the two are going to get added together. So in fact, if we, and you can see this a little bit here, in that what's going on is there's a layer that's called embedding tokens, which is going to produce a 1024 length vector out of 50,257 inputs. Then there's a pos embed, and pos, I'm willing to bet a lot of money, stands for positional, and an embedding pos, which is then going to take those integers that are produced by the pos embed and convert them also into 1024 length vectors. And then there's this combine thing here, which is going to basically combine the positional embedding with the content embedding, which is what I discussed in the prior video. We can actually see what's going on in the content embedding part. So let's actually see what happens if I content embed the Sally integers. And what you can see is it's going to produce I believe that's going to be a 6. I sat there with Sally, 1, 2, 3, 4, 5, 6. A 6 by 1024 matrix, of which the smallest value is negative 0.98 and the biggest value is 0.75. That's what that min-max business is. So then what happens? Well, then it also, as I mentioned, goes into this positional encoder, because it's going to try to add positional information to the content information. And so let's get that part of the network, and let's see what happens when I position tokenize the Sally integers. And it just produces 1, 2, 3, 4, 5, 6, because that's each, I is 1, sat is 2, there is 3. And now the next step is to figure out a way to render those 6 values as 1024 length vectors. Which seems like overkill to me, but whatever. And again, you're going to see that if I look at the positional embedding, it's a 6 by 1024 matrix. The values tend to have bigger ranges. They can actually be negative 2.5 to 2.5. But in any event, we're going to combine the content embedding information with the positional information, and that's done at the input combine level. And so what you can see here is as we emerge from the output, we're basically going to be taking the combination of content embedding, this is positional embedding right here, and content embedding, and the order doesn't matter because addition is commutative. And let's see, I think we should get, after all is said and done, a 6 by 1024 matrix. Hurrah. Okay, so that's the embedding. We're embedding both the words and information on their position. Now let's look at this whole attention layer transformer bit. So let's grab that whole decoder chunk of the feature extractor. And you can see it's a long chain of things that look pretty much like identical blocks. It does end with an N, and if I happen to know that that's called a normalization layer, that's the little iconography for a normalization layer, which basically tries to make it so that the mean of the data is 0, and I think the standard deviation is 1. All right, so what can we do? We have this decoder part. We can look at the graph of the layers. And I want to make this big because it's a big, complicated graph. I'm not sure I've shown you the layers graph feature yet, but it's going to turn it literally into a graph on which you can then use Wolfram language graph functionality. And it's a beast. All right, so this is a picture of sort of the flow of data through this network. And basically, remember I told you how these transformers are stacked multi-head attention pieces? That's what we're looking at. Here's one stack, here's second stack, third stack, fourth stack, and I believe it goes through 24 stacks worth before it ends up doing some final cleanup. So that's what's going on inside. This is what's actually going inside the deceptively simple picture right there. Okay, let's dive deeper. If you wanted to see what the input form of this looks like what you'd have to type if you actually wanted to type this out, it's enormous, and so I augmented tersed it. But you can see that there is a actual programmatic implementation of all this. All right, let's get that first block. Let's see what's in here. So I'm going to net extract it. Let's look at its layers graph. All right, and so you can see that this sort of looks like a blown up piece of that. And I don't know whether it helps, but here's another way of visualizing it. I've kind of turned it on its side, and you can see you start from this one point, you go out to all these 1, 2, 3, 4, 16 multi-dimensional or multi-heads. These are the attention heads. And then it finally all comes together, and then it goes through a little process of adding some stuff up. So maybe this makes it clearer as to what's going on inside the attention head. In any event, we ought to take a look and break it down even further. So let's look. We've really got two blocks here. We've got this first chunk here, which is where all the multi-head attention stuff is going on. And then we kind of have the cleanup block here. So let's look at those. This is a sort of a block, a big picture diagram of what's going on in that first block. And then this is a big picture of the much less complicated thing that's going on in this second block. I want to focus our attention on here because this is basically what we talked about in the prior video on attention layers. And so let's actually go look. You notice that it talks about how there's a norm chunk and an attention chunk. Let's go grab the attention chunk. All right, and we can look at this, and you can see it's kind of what we discussed, where you have input that's feeding into all of these attention components. The output gets sent to this catenate layer, which then goes into a linear layer that has a netmap operator working with it, and then you get some final output. This other thing is the query, and you remember how I said that in the Wolfram language implementation, the query is kind of broken out and dealt with separately, and so you see that here. So the other thing we can do is just look at one of these heads. I've picked head 7 for no good reason. So let's take a look at that. And this looks like our picture from last time. It's you got the query part coming in, you have a projection. Remember how you divide by the square root of the length? They're going to do that outside the attention layer, which is fine. That doesn't make any difference. And here we have the input going into a transformation for the key, a transformation for the value, both of those feeding into the attention layer. And I think what I mentioned, and if I didn't, I'll say it now, is that under the Wolfram implementation, they're sort of not doing quite as much work inside the attention layer and letting you do things like projection outside of the attention layer. But if you look at this whole thing as a block, it really is exactly what I described as an attention layer. And if you ever wanted to write one yourself, here's the code. All right, so that is we got to come up for air. That's the end of our deep dive into GPT-2. It is complicated, but it has very regular structures that I think with a little bit of effort can be understood. Now, I do think it's something of a miracle that this incredibly complicated beast actually works and that you can actually, do the back propagation to train it. But neural networks are pretty amazing, and GPT-2 is one of our biggest and brightest. Thanks for listening.